Hey there. Ever wonder why your AI model sometimes acts like it's stuck in a loop, or why it suddenly jumps to a completely different solution? Today, we're unraveling the math behind one of the most important tools in machine learning, stochastic gradient descent, or SGD for short. And we're diving into why it behaves the way it does near those tricky, critical points in the math of training models. Let's start with the basics. Imagine you're trying to find the lowest point in a mountain range, but you can only see a tiny patch of the landscape at a time. You take steps based on the slope you feel, but random gusts of wind, like noise in the data, might push you off course. That's SGD in a nutshell. It's a method that tweaks model parameters to minimize errors, but it's not perfect, because real-world data is messy. And that messiness, it's what makes SGD's journey so fascinating. Now here's the twist. SGD doesn't just wander aimlessly. It's influenced by the shape of the mathematical landscape it's navigating. Think of it like a hiker on a rocky trail. If they're near a sharp peak, a local maximum, they might get stuck for a while, bouncing around the edges. But if the terrain is flatter, a minimum, they might settle in quickly. The question researchers are asking is, how does the noise in the data affect whether SGD gets stuck, escapes, or lands in a different valley? The answer lies in the type of noise, and here's where things get really interesting. There are two main kinds. Finite-Variance noise, like the familiar bell curve, where extreme values are rare, and heavy-tailed noise, where wild outliers are more common, like sudden storms. The study shows that these noise types change SGD's behavior dramatically. With heavy-tailed noise, SGD is more likely to jump between valleys, like a ball rolling in a double well potential. It might suddenly leap from one minimum to another, even if it's supposed to settle in one. But with Gaussian noise, it's more predictable, staying put until it's time to move. But why does this matter? Well, it explains why training times can vary so much. If SGD starts near a sharp peak, it might linger there for ages, like a hiker stuck in a foggy patch. But with the right balance of noise and step size, it can eventually escape. The research even gives formulas to calculate how likely it is to end up in one valley versus another, depending on the width of the minima and the noise's properties. So what's the takeaway? SGD isn't just a simple algorithm. It's a dynamic process shaped by randomness and math. Understanding how it navigates these landscapes helps us build better AI. By tuning noise and step sizes, we can guide models to avoid pitfalls or explore new solutions. It's like giving the hiker a better compass for the journey. Thanks for watching. If you want to dive deeper into the math or see how this applies to real models, hit that subscribe button. And drop a comment below. What's one thing you'd like to see explained next? Let's keep exploring the wild world of AI together. Ever wonder why machine learning models sometimes get stuck during training? Or why they eventually break free to find better solutions? Today, we're diving into the fascinating world of stochastic dynamics, specifically, how optimization algorithms like SGD behave near critical points. Think of it as the sticking and escaping game that machines play when learning from data. Let's start with the basics. Stochastic Gradient Descent, SGD, is a workhorse of machine learning used to tweak model parameters and minimize errors. But here's the catch. When SGD approaches a critical point, like a local minimum, maximum, or saddle point, it doesn't always just settle in. Instead, it dances around, influenced by random noise in the data. This noise, represented by epsilon in the math, is like a tiny push that can either keep the algorithm stuck or help it escape. Now, the research we're looking at explores why SGD sometimes gets stuck and how it eventually breaks free. The key idea. Near critical points, the algorithm's path is a tug-of-war between two forces, the pull of the critical point itself and the push of random noise. The paper uses probability theory to model this interplay, showing how the algorithm's behavior changes as the noise, epsilon, becomes tiny. Imagine SGD as a ball rolling on a hilly landscape. Critical points are like valleys or peaks. If the ball rolls into a valley, a minimum, it might get stuck unless a gust of wind noise pushes it out. The research shows that as the wind gets weaker, noise decreases. The ball is more likely to stay in the valley, but here's the twist. If the wind is just right, it can nudge the ball out of bad valleys and into better ones. The paper uses something called stopping times, like checkpoints in a race. For example, if the ball's speed drops below a threshold, it triggers a check-in to see if it's in a good or bad area. The math proves that under specific conditions, the ball will eventually escape bad regions. It's like saying, if the wind isn't too strong or too weak, the ball will always find its way to a better valley. Why does this matter? It explains why techniques like SGD work so well in practice. The research shows that even with all the noise, the model's path is guided by underlying mathematical rules, like a compass pointing toward better solutions. This means we can design smarter optimization strategies to avoid pitfalls, leading to faster training and more reliable AI. So next time you hear about machine learning models learning, remember, it's not just about crunching numbers. It's about navigating a chaotic, ever-changing landscape with a little help from math. Thanks for watching. If you want more deep dives into the math behind AI, hit subscribe. And drop a comment. What's one thing you'd like to see explained next?